Hey class, we're going to continue on with 3.4 notes, looking at moving into the second derivative test. We studied a little bit with concavity in the first example, and now we're going to move on to how we can use the second derivative test to determine extrema. Now, we had the first derivative test before where we just, we found our critical numbers by setting the derivative equal to 0 and then finding where it's 0 or possibly undefined. And then we tested on either side to see if the function went from a positive to a negative first derivative or negative to positive, showing that it goes from increasing to decreasing or vice versa. So with this one, okay, what we're going to be doing, so that it says the second derivative test, let f be a function such that f prime of c equals 0. So that part's the same. First derivative, we're going to set it equal to 0, and that the second derivative of f exists on that open interval containing wherever that critical value was. Okay, so if f double prime, if the second derivative is positive, greater than 0, then what we'd have is a relative minimum. Now, I'll just kind of give a visual on that. The reason that we would know that is because if we have a positive second derivative, that means that it's concave up. And when a function's concave up, it's going to look more like this, right? So that's going to give us a minimum. If we're curving upward, that's going to give us a minimum on the graph. Now here, if the second derivative is negative, less than 0, then we're going to have a relative maximum because we would be concave down, curving down, okay? So that's how we can use that. And this is, especially if you're working with polynomials where a second derivative is easy to find, this test is useful because then you only have to test one specific point. You don't have to test on either side of that critical number. You can just test right at the critical number into the second derivative. And so that saves a little bit of plugging in if you have a simple second derivative find. Sometimes functions that like rational ones where you have to use the quotient rule might not be as useful to try to find the second derivative because it gets to be a lot of work. But polynomials are real simple to do a second derivative. So this one, for example, the first thing we want to do, start it like we always do. So we're going to find the first derivative. And we're going to get negative 15 x to the fourth plus 15 x squared. Oops, this was supposed to say to the fourth here. Okay, now we're going to set that equal to 0. Now with this, there aren't going to be any undefined values for our critical numbers, so we don't have to worry about that, but we could factor out negative 15x squared, and that would leave us with x squared minus 1, and that would factor a little bit more, x minus 1, x plus 1, and so my solutions, when I set it equals 0, I'm going to get 0 for the negative 15x squared I've pulled out, and then I'm going to get positive 1 and negative 1. All right, so I'm going to put those on my number line like I always do. Put 0 in the middle, and put negative 1 here, and put positive 1 right here. Now typically what I had done with the first derivative test was then I picked a number over here, like maybe negative 2, and then maybe I'd take negative half, positive half, and then positive 2, right? And so I have 1, 2, 3, 4 intervals to test, and I'd plug them into my first derivative, either form factored or whatever. But now with the second derivative test, what I actually want to do is I just want to test right at these critical numbers, but I want to test them in the second derivative because that's going to tell me the concavity. So based on that, I'll be able to tell, do I have a minimum or do I have a maximum? So I need to continue on with my second derivative. So f double prime. Now if I continue with that, I'm going to get negative 60 x to the third, and that would be plus 30x. Okay, so there's my second derivative. Now if I'm testing into my second derivative now, so now I'm going to take f double prime, and I'm putting exactly these values in, not in the intervals between them, but now I can test right here to tell if it's concave up or down. Okay, so I'm going to put in negative 1, and I'm going to test f double prime of 0, and I'm going to test f double prime of positive 1. Okay, so let's see if we can just do quick mental math here. If I would put a negative 1 into here, that's going to be negative 1 cubed is negative 1, making this positive 60, and then minus 30, so that would be a positive value. Okay, so I get a positive there. which means that I'm going to be concave up. So I'm going to be curving up at the -1. So we're going to look like that. Okay. When I plug in 0, I just get 0, and so that doesn't have a sign. So there we do not have a min or a max because it's neither concave up or concave down there. Okay, so we don't have an extrema there. Okay, and then at 1, when I put the 1 in there, that's going to be -60 plus 30. That would be negative, and so that means I'm going to be concave down right there at 1. Okay, so that means that I do have a min, relative min, at -1, and I'll have to plug that in to get the y coordinate, and then I have a relative max at +1. Okay, so if I were to plug those values in, if I put -1 in here, that's going to turn out to just be, so that'd be a -1 times -3, +3, and then this would be -5, so I would get -2 for that y coordinate. And over, if I plug in the +1, that's just going to be -3 plus 5, which would be +2, and so those would be my relative extrema using the second derivative test. Okay, so let's just take a look at the graph just to see that our results would be verified with what we did here. So this is the function that we were working with. So if I look at that graph, and I can see, something that looks like this. I don't know if this will let me touch it and get it exactly, but so right down here, I'd have to use the functions there. But what we can see, I think, pretty clearly is that -1 and then -2, there's my relative min, -1, -2. And right here at +1, +2, there's my relative max. And even though we had a horizontal tangent line here, that did not give us relative min or max. It continued to increase through there, which actually we'd find out if we continue on, we'd have an inflection point right there. But where we change from concave down to concave up, but yeah, that would be an inflection point, but it's not a relative min or max. And so where we got the second derivative giving us a 0 value there, that was neither concave up, concave down, so can't tell anything about the mins and maxes from that. Okay, and the next example, and these tables like this, the AP exam loves to have you examine numerically these different theorems, like first in these tests, first and second derivative tests. So here we don't actually have the function. We just have some input values, some output values, the first and second derivatives at those specific values. Okay, so part A says identify all x values where f has a relative minimum. Okay, now again, what we want to look for is where is that first derivative equal to 0 or undefined. Okay, so that's where we're looking through here, and I can see right here I've got a 0 and I've got a 0 here. Now something to be careful of here, if you're justifying your answer on numerical chart information like this, because we don't know specifically that it's a continuous differentiable function all the way through. And they just give us certain input values. We don't know everything that's happening. What we have to do here is the second derivative test is necessary here because we want to look specifically. Okay, so all we really know is here's information about what's happening with this function at x equals -1, and we know that it equals 0, so we have a horizontal tangent line. Now if we know that that second derivative is negative, then we know that it's concave down. And so because it's concave down there, I know that I've got a relative max right here when x equals -1, because I have a 0 from my first derivative, and now I'm seeing, okay, it's concave down because at that point I can see that we have a negative second derivative, so it's concave down. Now you might look at this and say, well, the first derivative too, because it goes from negative, which would be decreasing, to positive. That, you don't even see that really either. It goes to a 0. So it's it's hard to know exactly from the first derivative test what's really happening there. Okay, and so and actually, you know, it says identify where we have relative minimum. This one's going to be relative maximum, so I actually wouldn't even be answering necessarily that question right there. Okay, but over here, if I'm looking, you know, for the minimum, here's another 0, and because the second derivative is positive there, that means that we're concave up, and so that means right here I'm going to have a relative minimum there. So at you know, f prime of 3 equals 0, and f double prime of 3 is positive. And so to justify, I'm just going to say therefore by the second derivative test, we can say there is a let's see, what do they want here? Where x values, okay, so with just the x values, okay, there is a relative min at x equals 3. Okay, so I think we know, you know, by second derivative test, because we've got, you know, first derivative is 0 and second derivative is positive, therefore second derivative test tells us. Okay, so if we look here, you know, if we've got, if we know we've got 0 there, and then we've got a positive second derivative, we have a relative minimum. Okay, so we can see that by second derivative test. Okay, and then for our maximum, we kind of saw that already. You know, f prime of -1, sorry, f prime of -1 equals 0, and f double prime of -1 is negative. And for the same reasoning, therefore, by second derivative test, I'm just going to put s second derivative test, there is a relative max at x equals -1. Okay. All right. Next thing we were looking for would be x values where there would be an inflection point, and so we know that we're looking for inflection points, we're looking for where the second derivative would be equal to 0. Okay, and so I can see I've got, you know, right here at x equals +1, f double prime is equal to 0, so f double prime of +1 equals 0. Okay, and what else do we see? So we've got that possible one there, and we also have at 7 here, we have a second derivative equal to 0. Okay, so f double prime of 7 also equals 0. And here's the thing with this, guys. I mean, we can state where we see possible inflection points here, and I know we're looking for the concavity to change in it, and it does, but we don't necessarily, with these tables, we don't really know what's happening like right next to this x coordinate. Yeah, it went from here concave down to concave up, but you know, maybe it changed to concave up somewhere closer to 1, you know, as well, you know, on the left side, and then it was concave up and then stayed concave up. So I think all that we can say here is we can talk about possible inflection points, and so that's what I'm going to state. There are possible inflection points at x equals 1 and x equals 7. We can't say for sure with this this tabular information like this, because we don't really know what's happening right next close to it, and that's the reason why we can't really use the first derivative test on these either, saying that we're changing from, first derivative is changing from maybe positive to negative or vice versa there, because maybe that changed somewhere closer to that -1 x coordinate. We just don't know. So we can only talk about what's happening directly at that point, and we don't have any other tests to determine if it's if the concavity changed there. So I think all we can say is possible inflection points. And then for part D says write the equation of the tangent to the curve at x equals 5. That's pretty easy with what they give us, because at 5, well, we've got the ordered pair. We got 5, we got a y coordinate of 3. So we got 5, 3. And then the slope is given to us, right? First derivative at 5, that's going to be 2. So m equals 2. That makes it real easy for us. So y minus 3 equals 2 times x minus 5, or if you want, y equals 2 times x minus 5 plus 3 if we want to do that. Okay, so that's pretty straightforward. All right, so that is it for this section. Please try to